Hello, everyone. I'm Siraj Shah. I'm now retired and emeritus professor at the University of Alberta. I still do have some active research projects with colleagues at Alberta and also at the University of British Columbia in Vancouver. Um, I also have a visiting appointment at Hiroshima University in Japan with their Digital Manufacturing Education and Research Center. And that's about the introduction for me. So then I'd like to proceed, and I want to thank the organizers for inviting me to give this talk. The purpose of this seminar is to share with you over 2 decades of work done by my graduate students, research associates, and many collaborative projects with my academic colleagues. So let me start by saying that we are in the midst of some incredibly profound and powerful changes that are having an impact on the way we live, work, and play. No, I'm not talking about COVID-19. I'm talking about these transformative changes and the role that they can play in the safe and efficient operation of industrial processes. This seminar is about analytics in the process industry. Yeah. So let's start by discussing the terms that appear in my talk title. So I hope you can follow my cursor: big data and analytics, and is it more than just hype? And of course, all of this is in the context of a broad class of process industries. So to answer this question, let me first define a few terms, namely machine learning. And machine learning is a subset of AI. So simply speaking, big data is about analyzing large amounts of data using machine learning methods. AI is composed of many different fields or areas, and I only show a few areas in this slide here. Essentially, AI is software or algorithms that can reason, can infer, and think like humans. Machine learning, a subset of AI, on the other hand, is the science of getting computers to learn without being explicitly programmed. One can do this via supervised or unsupervised learning or reinforcement learning. And most of the applications that I will talk about involve simple applications of machine learning methods. Deep learning, again, a subset of machine learning, is when multi-layered neural networks learn from vast amounts of data. And neurons are part of a mathematical model that mimics how neurons work in the brain. So the next question then is the application of AI and machine learning more than just hype. And I present 2 viewpoints. The first one is from Mike Jordan at the University of California in Berkeley. Jordan is a well-known academic who has some valid critiques in the broad AI and machine learning area. And I quote I show you here some quotes from his article titled "Delusions of AI." So Jordan goes on to say that specifically on the topic of deep learning, it is largely a rebranding of neural networks which go back to the 1980s and the 1960s. So he explains it in the following way, says that it seems like every 20 years, there is a new wave that involves neural networks. And in the current wave, the brain processes information. In the current wave, really the main success story is the convolution neural network, more popularly known as CNN. And he goes on to also say that deep learning claims that it is taking advantage of an understanding how the brain processes information, how it learns, how it makes decisions, or copes with large amounts of data. And his claim is this is not exactly true. Remember that a neuron in a neural network algorithm is a linearly weighted sum that's passed through a known linearity, and the human brain does not quite work like this. The second quote is, he says, data analysis can deliver inferences at certain levels of quality, but we have to be clear about what levels of quality. And this is fair. So we really need to have error bounds around all our predictions. And this is something that's missing in much of the current machine learning literature. In the last quote, and I won't read it, but essentially, Jordan and many other critiques have discussed this, and we call this the observability issue. And what it means is the following. When you want to draw inferences from data, a natural question to ask is, does the data have the information that you're seeking, or can you give confidence bounds on the inferences that you will draw from the data? So as a counterpoint to Jordan's comment, the second viewpoint is from Professor Venkat Subramania of Columbia University in New York. And the quotes that I will show you are from an article titled "The Promise of Artificial Intelligence in Chemical Engineering." Very aptly titled, "Is it here finally?" So Venkat goes on to say that he's a bit wary of the hype surrounding the new phase. However, for many reasons, it does seem different this time. And then he goes on to say, we're witnessing the dawn of a new transformative era in the management of different types of knowledge. And so overall, Venkat is cautiously optimistic on the application of big data. But he does caution that much work remains to be done, particularly in the area of information fusion from many different sources of data. And so that's the second and the third bullet that I've shown here. The breakthroughs for successful applications of AI would require going beyond purely data-centric machine learning methods and leveraging other representation, knowledge of the process and reasoning methods to come to arrive at successful applications of AI. So the other question is, why is there so much interest from industry to do analytics? Three main reasons. First of all, engineers are now treating data as a resource, and certainly availability of vast amounts of data. Secondly, we now have access to powerful machine learning, deep learning, reinforcement learning algorithms, and faster computers. So where is the data explosion coming from? So here is a graph of IoT connected devices worldwide from 2015 to the prediction at 2025. So what you see here is that the total installed base of IoT connected devices is projected to be 75 billion worldwide by 2025. So that's a 5-fold increase in 10 years. The process industry, of course, has a lot of archived data, and IoT and the industrial Internet of Things devices are also making significantly more data available. The large increases anticipated in IoT connected devices is also because of 5G, fifth generation wireless networks. And I also want to point out that interest is growing in developing neural network solutions to deploy machine learning even on low-powered IoT devices. And to convey the challenges that we face in working with vast amounts of data, I looked for an image that would express this idea clearly, and that of a digital tsunami. The torrent of data that we find ourselves engulfed in, lots of data, but needless to say, many challenges in dealing with such data. And so it's important to remember that data comes in many shapes and many colors. What I mean by this is data comes in many different formats, data formats, and many different data types. So for example, one may need to work with spectral data from infrared spectroscopy analysis. You may need to deal with data in the temporal, spectral, as well as spatial domains. For example, 2-dimensional or 3-dimensional data feeds that you would get from a paper machine or a steel mill. You may need to deal with clustered alarm flood data or data from acoustic and vibration sensors. So these are not your musical notes, okay? You may have to work with image data, for example, for sensing purposes. And you also need to combine all of this information with process topology, process connectivity information. And finally, you have to combine all of this information with business and financial data. So the challenge is to fuse data from many different sources and how to engineer a software platform that would enable one to do all of this. The other important message that I wish to convey in this slide is that unless you're armed with the right flotation aids, what I mean by this is unless you're armed with the right analytic tools, you can easily sink in the sea of data. Okay. So here is the agenda for my talk. I already talked a little bit about this. And what I want to say is that this is not a scholarly talk. It is a perspective talk, mainly with references on most of our own work and supported by simple applications of analytics to give you insight on the past and current field of analytics. The last part here is on the application of analytics on simple experimental processes. The illustrative examples will involve temporal and spectral data analytics. I'll show examples where we have worked with image data, vibration, acoustic data from vibration sensors, and I will also discuss the application of analytic methods on a number of industrial case studies. Okay, so let's ask the question, or let's define, what do we mean by process data analytics? It is the discovery and purposeful utilization and communication of meaningful information and patterns in your data. Now, when you read this definition, and those of you who are control engineers will argue that control engineers have been doing real-time analytics on large-scale processes for many years. In digital speak, or the jargon of analytics, we've been doing online analytics with decision support. For example, feedback control, model-based predictive control, real-time optimization, developing and using soft sensors or inferential, performance monitoring, fault detection and isolation, and so on. So we've been doing online analytics for many years, and yet we've not really increased the level of autonomy in running our processes. Why is that? Have we been overly complacent? And so the natural question to ask is, what should the new generation of process analytic tools offer? What is missing? Okay, so let's see if we can answer that question. And generally, when we talk of analytics, we are primarily working with sensor data. But this is really a disjointed view of the process. One should consider all data in unison, meaning combine information from all data silos. So for example, you also want to use alarm and event data. Such data capture expert information on how we handle near misses, mishaps, accidents, and therefore use this information in predictive and prescriptive modes to prevent major disruptions and accidents. And in addition to this, you also need to combine this, you also need to combine this with database connectivity or process topology information to figure out the material and information flow paths of the process that is being analyzed. And of course, you want to also incorporate domain knowledge and such expertise about the process. And so really, this is the challenge of information fusion from many data sources. So, and in fact, let me go back. So this, I feel, is the most important takeaway slide in this talk. The main message in my talk then is that there is a paradigm shift underway in process operation. It's important to do information fusion from many different data sources. And so I say, listen to your data and use it to monitor the performance of your process. And I use the term listen as a metaphor. Process your data, explore, visualize, slice and dice your data to extract information and knowledge from the many disparate sources of data. The main idea is to leverage and maximize value in the data that's sitting in different silos, namely sensor data, alarm and event data, and causal process knowledge, and of course, other domain information as well. Okay, so fusing data and extracting information from all of these sources will be a game changer. It represents a major paradigm shift in how we should be looking not just at sensor data, but alarm and event data, process topology information, and domain information as well. Okay, all right, so the rest of the talk, so I've done all of this, the rest of the talk is the application of analytics to demonstrate what is possible. So let's start by looking at controller performance monitoring. The ideas behind CPM that our group and others have developed, and these ideas are used to monitor thousands of control loops. To do this, you need to analyze the time series of the process variable over a given time period. And the main purpose of this tool is to detect poor performance and then do diagnostics. You want to figure out if the control loop is delivering the performance it is capable of delivering. Much of the theory and the practical ideas in the application of this technology are in our book and subsequent papers that I quote here. Okay, so performance monitoring and feedback control is all about reducing process variability that I show you here. So the idea is to reduce process variability and thus deliver products on spec and also at reduced energy cost. So here is a typical application of CPM, controller performance monitoring. This one is on a benzene plant. And I show you here data from 36 different control loops on this benzene plant. The blue trends correspond to the process variables, and superimposed on the blue trends sometimes are the red trends that you can see. Those are the set point values. So for each one of these 36 loops, we obtain a performance index, and a performance index near 1, close to 1, indicates very good control. A performance index less than a threshold, say 0.5, 0.4, indicates poor control. Roughly, of the 36 loops, this will tell you that 12 out of those 36 loops have poor performance, and for each one of these, we can do the diagnostics. So this is how CPM is being applied, and I show the results here. So this technology has been widely embraced by the process industry. It is now a well-accepted practice, and industry is using this very proactively. So the examples are that BASF, at its Ludwigshafen site in Germany and at its Antwerp facility in Belgium, is monitoring more than 40,000 control loops. Likewise, Saudi Aramco is also deploying CPM on thousands of loops and many model-based predictive control applications. Some of these details appear in this book titled The Impact of Control Technology. And I also want to mention that the key players in promoting this technology have been Tom Harris at Queen's University, Bia Huang at Alberta, and of course, Nina Thornhill at Imperial College. Okay. I now want to discuss how these ideas of performance monitoring can be combined with other things such as adaptive control. So we're going to combine controller design, online controller design, or more or less adaptive control with online monitoring. And let me then illustrate this idea. So generally, this is a simple block diagram of an adaptive controller where you want to adjust the controller settings, ideally only when controller performance is poor. But that's not how adaptive control works. Adaptive control will do identification, online recursive identification, and will update the parameters at every sample interval. If you build a performance monitoring tool on top of the adaptive controller, then you can ask the question, is the performance good or not? If it is not good, then you can turn the system identification, and only then you want to turn the system identification block on and update the controller parameters. On the other hand, if performance is good, you then want to let the controller do its job, let the status quo prevail. So this is the basic idea. And the reason I mention this is that adaptive control now is being reinterpreted as a reinforcement learning strategy and attracting a lot of attention. So let's see the application of this on a simple pilot scale heater. So I show you here a tank heater where water is being heated by a steam coil. Steam is the manipulative variable, and we measure the temperature of the water either at thermocouple number 1 or at thermocouple number 2. When the temperature is measured at thermocouple number 2, one would expect a significant delay because of the long pipe and the transport delay due to the flow rate of the water in this pipe. So when you switch, so initially for the first 8,000 seconds, we're going to use thermocouple 1 as the sensor signal for this control loop. And thereafter, we'll switch to thermocouple number 2. So when you switch from TC1 to TC2, the control task would be expected to be more difficult because of the time delay. Here is a picture of the equipment as it exists in the laboratory at the University of Alberta. And here is the actual experimental result for fixed proportional integral control. What you notice is that control degrades significantly here when thermocouple number 2 is used as a sensor because of the large delay. Control loop becomes highly oscillatory. However, if we impose performance monitoring as shown here, so we will turn on the adaptation when performance degrades below this PI, performance index of 0.6. So here is the measurement of the performance index. We start with 0 initial conditions, so of course, controller and the adaptive mechanism is turned on at this time. As soon as performance exceeds the threshold, adaptation is turned off. And then here, when we switch to TC2, adaptation is turned on again. And here is the result. So what you see is that satisfactory control is reinstated quickly with online monitoring and adaptation. So this is an example of fault-tolerant control or fault detection and isolation with remediation, where the process suddenly encounters a fault, in this case a sensor problem, with a large delay, and it is able to detect and take instant remedial action to counter the effect of such a fault. And these data-driven control techniques, these techniques require a confluence of several methodologies: monitoring, identification, optimization, and adaptive or reinforcement learning method. Okay, I now want to look at a second application. This is the application of spectral data analysis on vibration sensors to detect gear faults. And this simple application, or let me go back, this simple application is to illustrate the use of spectral and wavelet transform data for fault detection in a rotating machinery. And by the way, rotating machineries such as turbines, compressors, and pumps are expensive machines that require careful monitoring and diagnostics. So let's see how we can do this. What I show you here is a simple time series of sinusoids. We have a low frequency sinusoid, a high frequency sinusoid, and a mid frequency sinusoid. And if we do a fast Fourier transform, we see the three distinct peaks corresponding to the three different sine waves. The downside of fast Fourier transform is if you only work with this, then the time localization is missing in the spectrum plot. And mind you, you see the sinusoids very clearly, but they could easily be buried in noise, and then you would not even be able to see the time localization here. So what we'd like to be able to do is how to process these waveforms, this data, so that you can see everything clearly. And to answer that, we look at wavelets. And here is the wavelet processing on the same signal. And what I want to show you here is wavelets will now preserve the time localization as well as the frequency localization. So this is the time axis. This is the inverse of the frequency axis with the amplitude. It clearly says that for the first 128 samples, you had low frequency sine wave. For the next 128 samples, you have high frequency sine waves and so on. So we now want to apply this to this gearbox rig located in the mechanical engineering department at the University of Alberta. And what I want you to notice is the vibration sensors mounted on the housing of the gearbox. We'll get to look inside the gearbox shortly, but these are the vibration signals that we're analyzing. So here is a peek inside the gearbox. We will look at different faults in these gears and see if we can detect and identify those faults. So data was generated for the following 4 conditions: gear with normal teeth, gear with a chipped tooth, with a missing tooth, and then a combination of chipped tooth in one gear and a missing tooth in another gear. And the gears were mounted on different shafts, each one rotating at different speeds, okay? So here is the picture of those gears. This one has a chipped tooth, has a missing tooth, and a combination of a chipped and missing tooth. So when you do wavelet transform of the vibration sensor data, the normal gear wavelet transform looks like this. We've scaled everything. And for the chip case, remember, now notice this scale is exactly the same. So you can clearly see the difference. And these 2 peaks corresponding to the rotating speed of that gear indicate a chipped tooth. A large peak indicates a missing tooth. And when you look at the combination of chipped and missing, you would expect these 2 peaks to show up here, which they do. So this is an example where machine learning methods engaged in a supervised learning framework can use these signals as fault signatures and thus detect and diagnose the faults. Now, there is an alternative method that can also analyze vibration data, and that method is support vector machines, or SVM as they're more popularly known. And we're going to apply SVM to also detect and diagnose faults, different faults in the gearbox. Now, this one has a 25% crack in the tooth, 50%, you can see the numbers here, 75% crack, 100% crack, and then you have a completely missing tooth. So we're working with the same gearbox, and the reason behind using support vector machine was that this is one of the earliest embodiment of machine learning methods. They were developed in the 1980s, and these methods have been applied in image identification, say for example, by the US Postal Service for reading zip codes. And what they do is not only can they detect the fault, but they can also quantify the extent of the fault that I show you here. So for normal gear, the SVM metrics, the fault metric, if you can say this is the fault metric, essentially hovers around 0. With a small crack, it goes over 0, and with 50% crack, again, higher than here, and so on and so forth. So this slide essentially shows that you can not only detect, but you can also quantify the extent of the fault. Okay, I now want to discuss the use of image data and image analysis to develop a soft sensor to estimate the interface level in a line 6 separation cell at Suncor Energy. Okay. All right, so here is a picture of the separation cell, a schematic of the separation cell, where we're interested in measuring, getting an indication of the froth bitumen and the middling, tailing middling layer. You can see the froth bitumen through a side class that I show you here. And the idea is to regulate this layer at a desired point to avoid losses of oils to the tailing ponds. So that's a big environmental win, okay? So here is the image that the camera-based soft sensor uses for interface level estimation. The dark layer is the bitumen layer, and the white layer is the tailings, middling tailings layer, and here is the interface across the two side classes. And on the right is the top view of the separation cell at Suncor Energy. The lighter bitumen froth overflows from the tank, from the top of the separation cell, and it is transported for further processing. Here is the picture of the tank. This is a very large tank, 60 feet in diameter, 64 feet high, conical tank, and each tank processes over 100,000 barrels of oil a day. So we developed a soft sensor for this. I'll show you the details and use that information for feedback to manipulate the tailings pump speed. Okay. The end result, if I can say this early before showing the result, was a robust and successful image-based soft sensor. And it was based on, we tried a classical Kalman filter. Here is the actual interface, side class view that you see. Here is the black and white converted image. And we feed this information to a Kalman filter. And because the Kalman filter assumes Gaussian noise for process noise, it was not able to converge to the right interface level. Okay, the Kalman filter did exactly what it's supposed to do. It hedged between two distributions. This is the main interface, and here is additional noise because of the reflection from the side class and also sand particles in the froth bitumen. On the other hand, when we apply a particle filter, the interface level is tracked very well. All of this noise is discarded, and this served as a very good image-based sensor. And here is the result, the closed loop result with the new image-based sensor allowed excellent bitumen middling interface level regulation, shown by the red line. The blue line shows the pump speed, so the significant reduction in the variability as opposed to what I show you on the left side here, where we were using an old unreliable sensor with significant variance in the pump activity. Okay. All right, I'm almost at the end. I want to now discuss, emphasize causality analytics. And for this, we're using information theory-based approaches for causality capture. And I want to credit the work that I'm going to share with you, the work of past graduate student Duan and Hu, with my academic colleague Tongwen Chen. All right, so let's ask the question, what is causality and why do we need process connectivity or process topology information for doing root cause analysis? And the answer is detection and diagnosis of plant-wide abnormalities and disturbances. These are major problems in the process industry. A simple fault can easily propagate along material and information flow paths in the process. Remember, modern plants are highly interconnected and integrated to save energy. So a small fault in a loop or in a unit can easily propagate to many other units or many other control loops. Okay, and to determine the root cause of an abnormality, we need to know the connecting pathways of how the fault is propagated in the plant. And by the way, the cause and effect analysis, the causality analysis that we will perform, this is also used for Hezop analysis. I won't dwell on this anymore. So here, so we apply this idea on this benchmark problem from Eastman Chemicals to illustrate the application of these methods to find the root cause of plant-wide oscillations. The black dots that I show you here indicate control loops where oscillations were observed. And here is the data from the plant. This is the time trend of these loops. Here is the corresponding power spectra of these loops. And what you see are common oscillations in these 8 loops here, 4 and 5, 6, 7, and 8 loops here. They're all oscillating at a frequency of about 0.003 cycles per sample, almost a 2-hour period. And our goal was to detect and diagnose the root cause of this oscillation. We applied a transfer entropy method for causality detection. So the 8 loops that we identified as having the same oscillations, we were able to obtain connecting pathways between those 8 loops. And if you unscramble this, untangle this, this is the picture that you get, where the red line shows the bidirectional cause and effect relationship between these loops. So essentially, when you see this figure, it confirms that level controller 2 is the likely root cause of oscillations in all of these 8 loops. And in fact, this was confirmed by Eastman engineers that yes, it was the level control loop 2, which was the cause of oscillation. There was a sticky valve in this level loop, which resulted in limit cycles, which then propagated to all of these other loops. The next and the last application that I want to share with you, this is an industrial application, shows the use of sensor data and alarm data. We are fusing information from both of these data sources to determine the abnormality pathways. So we are going to do causality detection using first alarm data and then try and determine the root cause of the abnormality in this next application. So we are really fusing information from several data sources to determine the root cause of this abnormality. So what I show you here, and this is data from ABB, this is the high density alarm map for 30 alarm tags. These are rank ordered from the worst bad actor to the second worst bad actor and so on. And so if you look at the first bad actor, here are each pixel here, hard to see the pixels, but each pixel here corresponds to 10 minutes of alarm data. So for example, at this point here, the orange line, this is roughly 15 or 16 alarms over a 10-minute period, okay? And what you also notice is that many alarms light up simultaneously at the same time, indicating a very big process upset that the operators have to identify. And they need to find what is the root cause and take action to mitigate this disruption. So I next show you a plot of the accumulated, the total number of alarms with respect to time. This is over a 12-hour period, and that highlighted region that I showed you in the previous slide corresponds to this blip here. The threshold of 10 corresponds to the ISA and the IEC standards, which says that anytime you exceed you have more than 10 alarms over a 10-minute period per operator, that's the announcement of an alarm flood event, and you want to take a look at what caused this flood event. Okay, so we want to find out the abnormality, the root cause of the abnormality that caused this event. And for this, we're using binary database causality analysis. Now, I just want to point out, social media methods routinely use causality, the binary database causality analysis to monitor the spread of messages. For example, to check how and where information spreads. For example, you know, how does the tweeting activity spread from one source to another? So we're going to modify these methods to determine how one alarm triggers more alarms and thereby develop a connecting pathway. Okay, so here is that high density plot. So we look at these 30 alarm tags and we find connecting pathways between these alarms, and we obtain these subnetworks where alarm 5 triggers alarm 4, which in turn triggers alarm 31. Here is another subnetwork, 7 triggers alarm 10 and 11. And here 1 triggers several alarms, 15, and these ones here. So when you look at these subnetworks, the likely root cause of the oscillation, the alarms that trigger the abnormality. Sorry, there are no oscillations. The alarms that trigger the abnormality are the ones at the very top. So these are the 11 variables. And for each one of those 11 variables, we find the corresponding process variable tags. We then do causality detection on those 11 tags, 11 process variable tags, and we obtain the following connecting pathways between those 11 tags. And this pathway tells us that the likely root causes of those alarms is either process variable 3 or PV1 or PV5. It cannot be PV2 or PV7 or any one of these variables, because the arrows all go down. There are bidirectional connection between these 3 variables. In fact, these 3 process variables form a loop for a pressure control, for the pressure controller, and the fault in this control was indeed the root cause of the studied alarm flood. Okay, so the steps are: look at the accumulated number of alarms, get a tangled web of connection between these 30 variables, untangle them, shortlist to smaller networks, find the corresponding process variables, and then obtain a flow path between these variables to arrive at the root causes. And by the way, more details on this work appear in this paper, which was presented at the 2017 IFAC World Congress. All right, okay, so just last couple of slides on visualization. The field of visual analytics is important and certainly useful in conveying information very effectively. Alarm data is binary, not interesting to display as a trend, but a different measures of alarm flood, such as different measures of alarm, such as flood, can reveal quite interesting information. So what I show you here is alarm flood data over a 24-hour clock, this over 90 days. So the inner concentric circle is alarm flood data for day 1, day 2, and then this is for the 90th day. And the orange bars correspond to the flood events. And what you can see is most of the flood events occur during this time in the morning from 9 a.m. to 3 p.m. and so on. Again, you can consolidate all of this information in this graph, which is again on a 24-hour clock for over 90 days. We've accumulated all the information. And again, this confirms that most of the flood events occurred during this period from 9 a.m. to 3 p.m. or 4 p.m. All right, so to finish up, I want to summarize, and important to analyze sensor data, alarm data, and process connectivity information for safe and optimal process operation. The studies that I've shown illustrate the value of information fusion from several data sources. And I've demonstrated that machine learning methods do have a role to play in process data analytics. And I again emphasize, listen to your data, process, visualize, explore, and analyze your data in temporal, spectral, and other domains. Don't treat data as a black box. Combine this with a priori process information, domain knowledge, and so on. And a lot of work needs to be done in the automation of process connectivity information from process data. This is certainly very useful for root cause detection. I don't know if I have time. I just wanted to pitch to the younger listeners, if there are some, to say, if you want a challenging, interesting analytics problem, try agriculture. Why, you might say? Well, the world population is supposed to increase from 7.6 to 9.8 billion. We'll need more food. And for that, we need to have smart irrigation to conserve fresh water, and we need sensors for soil moisture and nutrients. And for this, you need to treat crop growth as a batch PSC process. So using agrohydrological models that are crop and zone specific, you can consider, corn or wheat over an average 3 to 4 month growth cycle. From sowing to harvesting, you can consider this as a batch process with time varying dynamics. And during this batch growth cycle, you need decision support systems to ensure the right amount of water and nutrients for optimum process sales, just as in a batch chemical process, a polymer process, or a pharmaceutical process. And for this, you will need sensors driven by machine learning and convolution neural networks to determine the water and nutrient needs. And remember, these are crop and zone specific. So no two farmer fields will have the same sensors work consistently. And using drones or satellite imagery data, you can develop soft sensors to monitor water and nutrient needs and so on. Okay, so sorry, I kind of almost took a little bit longer, but I do want to acknowledge the work of my graduate students and research associates. Many of the names I did mention in the papers that I quoted, but there are many other students who really contributed enormously to the work that I've shown here. And I also want to acknowledge the funding support from various agencies and industry, and also data access from Suncor, Eastman Chemicals, and ABB. Thank you, and I'm happy to answer questions. All right, so I will start from the first question. This says, why do I shift from TC1 to TC2? Oh, this is regarding the adaptive control application with the performance monitoring that I shown. Well, yeah, we were doing this to see if the controller performance monitoring and the adaptive idea would work or not. Yeah, ordinarily you would not, but let's suppose if the sensor would fail, then you would want to connect to another sensor. And by the way, this is possible using wireless sensors. You can do loop connections on the fly, all right? Okay, so the second question is from Sandro. Would I drive a car with those many alarms as in the ABB slide? If not, why should we design and tolerate an operation and tolerate in operating plants that are so bad? And agreed. But and yet, Sandro, that data is real data. I mean, we have not simulated that data. That data came from industry. The answer to your question really is, I think we're operating plants in an over-alarmed state, meaning in the old days, each alarm had to be carefully hardwired, and there was limited space because the alarms were wall mounted. With digitization, it has been very easy to alarm. All you need to do is flip on a switch, and thereby we have many more alarms than we really need to have. So that is the main reason. All right, so the other question is, what software package can you advise to use in process data analytics visualization? Really, we have developed our own package, but this is not something that you would want to use in industry. You know, it is an academic package where we are using MATLAB as a platform, which allows you to do data visualization, also allows you to look at sensor data, allows you to look at alarm data, and to an extent, causality, database causality detection, but on a very small scale. Okay. All right, another question. How do we arrive at the root cause in connecting pathways? Do we use graph theory algorithms? So yes, you can use graph theory algorithms. So the application that I showed you, the two applications, the one related to Eastman Chemicals and the other on the ABB data set, those were done. We arrived at the pathway using causality analysis, in one case transfer entropy, and the second case binary database causality analysis. And then we manually concluded that the root cause of the abnormality in both instances were the loops or the variables at the very top. I'm not sure if that answers the question. If not, please do get back to me. Yeah. Okay, another question. Can the result of machine learning and analysis be used outside of the scope of training data? And how to assess the reliability, safety in that case? Well, typically what you do using machine learning methods is you divide your data into a training data set, a validation data set, and then finally a test data set. So you really train your machine learning algorithms carefully, and then you use the validation data set to tune the hyperparameters, the fine-tuning nodes for machine learning to see if it indeed does work well. And thereafter, you try and apply, you test the machine learning algorithm. And this is where you get an indication of the reliability and safety. So there will likely be false alarms as well as missed alarms as well. None of these methods will give you 100% accuracy. But what I say is, if you're trying to detect, proactively predict the onset of faults, and depending on the application that you're working toward, some answers are better than having no answers at all. Okay. Another question. In your opinion, is the chemical engineering role is limited to just analyzing industrial data using different machine learning and visualization tools, or it must also include some kind of IT related training, e.g. cloud computing, high-speed performance? Well, I think the role of the chemical engineer is very important. It is becoming more multifaceted now, and depending on the application and the area of work, yes, you have to, of course, know basic engineering. You need to understand your process very well, but you also need to understand the limitations of the machine learning methods, simple regression versus sophisticated convolution neural networks. You need to understand the limitation of these techniques. Do you need to know cloud computing? Well, many a times, many of these applications are now located in the cloud. So you need to access information and applications in the cloud. I don't think you need to know cloud computing. I don't think you also need to know high performance computing unless you're using very sophisticated image identification, you have image identification problems and so on. Okay, another question. The emergence of Python and other open source analytic coding toolboxes have significantly lowered the subject matter knowledge required to use them, sometimes with good end results and sometimes not. Any comments on that? Surely, yes. Python and Julia and all these notebooks are certainly very useful, and I am very much in favor of using these as tools. And by the way, many of the functions for machine learning methods are available in Python and other open source analytics software. So by all means, use what you're most familiar with. And increasingly, the advantage of open source software is you can easily share information, ask for help, and so on, and that's easily available. Okay. Another question on how to include the operation limitations in process control diagnostics that are not in the form of data. to reflect recommendations that can be implemented industrially. I'm not sure if I understand this, but yes, we do have limits on the manipulative variable. For example, there are constraints. The valve can only open up to 100% or close to 0%, for example. So those limits are, for example, using MPC applications, those limits are respected. And if you're doing performance monitoring, for example, on an MPC application, and if the MPC application does not deliver the performance it is supposed to, then you have to ask the question, are your constraints really responsible for the poor performance and so on? So you can build on your dashboard, you can build numbers which will indicate to you if you've been violating constraints or if you're at constraint limits when you are attending to a specific abnormality, as an example. Okay, so a question from Bhavik. I mentioned the importance of fusing information from various sources. It seems that Bayesian method should be a rigorous way of doing this. What is my opinion about these methods and the research challenges? Yes, there have been many applications of Bayesian methods on this, but I'm not sure if Bayesian methods can work with, for example, categorical and text data as efficiently as some of these other methods would work. I know, Bhavik, you worked with Bayesian methods, and my colleagues also have worked with Bayesian methods. And increasingly, you're also reinterpreting Bayesian methods. Many of the machine learning algorithms can be reinterpreted from a Bayesian point of view. So there are certainly research challenges, and I may be able to point you to some of the work that's being done in this area. I don't have often the information. Okay, another question. Is there any technology concept which helps in fusion of numerous data sources along with topology representation to track and do causality analytics? And how advanced is the work on network analysis in this case? Where there have been various approaches used for causality capture. There is very active work in this area. You can also refer to our book, which came out just a few years ago. I did not mention that, but it is Causality Capture in Industrial Processes, where we are saying, we're comparing different approaches, including XML and other graph-based methods to capture causality. Now remember, a lot of this information is available in the piping and instrument diagrams, but very hard to digitize, at least not yet. I know there are people who are working toward these ideas. So that's all I can say. All right, can R software, another question, can R software be used to do data analysis and process industry? Yes, R is a common platform that's used, and again, open source. So just like Python and other open source software, very useful. It is more statistically based, the R software, and again, there is a lot of help from the open source community. Okay, question from Dominique. So the questions, Dominique says, nice practical case studies, technical solutions involve considerable engineering insight. Certainly, yes. In contrast, people expect that ML will provide answers automatically. And the question is how to automate the process that is, meaning how to make it systematic. And yes, Dominic, you're completely right. These studies that I showed, they are PhD projects, involved a lot of work. And I have to say, none of this was automated, at least the last part, meaning the arrival of the root cause of the abnormality, the plant-wide oscillations, as well as the problem, the abnormality in the ABB data case, it was not automated. We had to work on it manually. The challenge is to see if we can develop rules using machine learning methods that would give us, that would allow us to do this systematically. So certainly, yes, that's work in progress, and it's a good project for a PhD student. Okay, another question. Controller performance monitoring placed above the system identification is similar to or based on the idea of model predictive control? No, not really. I think model-based predictive control is completely different. And yes, you can also put a CPM, a controller performance monitoring module, on top of MPC. So no, MPC is different. MPC assumes that you have a model of the process, a multivariate model with constraints, all the information on the constraint. And so that is different. Okay, I think, all right, so one more question. For the beginners, what tools and softwares they can learn to understand process analytics? And I suggest, again, look at papers. I don't know if there are any books yet. I know there are quite a few examples. We ourselves and my colleagues are working on some of these, but I suggest look at papers. And the other idea that I would suggest is start with a simple problem, a well-defined problem, an abnormality that you would like to attend to discover and to be able to predict, and see if you can build a machine learning algorithm to predict and detect that abnormality. Okay. Okay, another question from Monsef. Yeah, it's a good question. How to deal with the lack of labeled data, imbalanced training data. Very important. So an important part of machine learning, when you divide your data into training, validation, and test phases, is you have to ensure that the data that you're analyzing is well balanced. So for example, if you're looking for a fault, then the number of normal data sets in your training phase should be roughly 50%, and you should have 50% of fault data set as well. Typically, we don't have a lot of faulty data. We have almost 95% of normal data and very few faulty data. And so that would be an imbalanced data stream. So it's a very valid point. In fact, we are working with an interesting problem with my colleagues and students at UBC, where we really had a hard time in getting a balanced data set. But you do have to work on a balanced data set for sure. Yeah. All right, another question. How can process engineers with 2 to 3 years experience develop their knowledge in process data analytics? And I suggest learn to work with simple machine learning techniques. Regression, least squares regression is a very simple, you can call it a machine learning technique. Start with that, curve fitting and so on, polynomial curve fitting and so on. Start with these ideas. Obtain simple models of your process. Simple models of your pump, for example, would be a good way to do things. I didn't have time to discuss the digital twin idea, but we worked on digital twin ideas for pumps as an example. Pumps typically have a normal operating trajectory depending on the RPM that you operate your pump. So you already have a model of how the pump should operate. And then you can compare the operation of the actual pump with what is expected. And that is a very simple example of working with a very simple problem and getting experience in process data analytics. Okay.
Sirish, we have one more question submitted in the chat box, and it is, please could you talk about reducing variables in the analysis? What care should be taken to do so?
So, Sarah, if I can repeat, so how to reduce variables in the analysis?
Yeah, what care should be taken to do so?
Sure. Yeah, no, good question. So I think this is related to causality detection, whether it be process variable data or binary alarm data. So the reason to reduce the number of variables to analyze, you need to shortlist, because the transfer entropy approach or any other causality cause and effect analysis approach is very computer intensive, takes a lot of time. So you really need to shortlist variables. And the way this was done in the first example for the Eastman benchmark data set, we looked at the spectral data to arrive from 14 to just 8 variables, which were oscillating all at the same frequency. And the reason is the variables with the highest amount of energy are likely the root causes. Those show up in the spectral trend. For the binary database causality detection, remember we had 30 alarm tags and we narrowed those down. So we only looked at alarm tags corresponding to the strongest causal relations. Details of this appear in the papers that I listed, and I'm assuming this will appear, you'll be able to see a recording and you'll be able to see those papers, or otherwise email me and I should be happy to provide you with the references where you have these details.